Okay, we're going to be doing some prototype problems, and to get the best results from these prototype problems, whenever a question is asked or a calculation asked, if you'll pause the video and try to do the calculation yourself before actually going on to the answer, then you'll get the best effect out of these problems or the prototypes. All right, we're looking at Newton's second law with a known acceleration. In this case, a rotating Ferris wheel. We're asked to find the normal force the seat exerts on the person and to use vector notation. So the first thing is, let's draw a free body diagram. And I show the free body diagram with the normal force, of course, pointing up, the gravitational force pointing down, and the centripetal acceleration pointing toward the center. I also denote the XY axis. Now, go ahead and write down what you think is Newton's second law governing this behavior. Just pause the video and write down your answer. Okay, here's Newton's second law. We have, of course, the sum of F equals the mass times acceleration, where Fn is in the positive J direction, plus the force of gravity, which is in the minus J direction, and the centripetal acceleration points toward the center of rotation, which in this case, with the person being at the top, points in the minus J direction. Okay, go ahead and calculate the normal force based on Newton's second law. And here we have our normal force. Fn is of course in the J direction. We can solve for it based on this equation right here. And that means that minus mj in the minus j direction plus the mass times acceleration centripetal in the minus j direction is equal to the force of gravity mg minus the force of the acceleration in the j direction. And we can go ahead and substitute in the numbers. So calculating AC, of course, remember what AC is, centripetal acceleration, how it's related to the velocity and the radius. And we can calculate that as v squared over r equal to 1.67 meters per second squared. Now let's finish the calculation because we've got to take this number here, and we of course want to just put it into AC over here. And we come up with 732 newtons. And you can compare this to the actual weight of a person, which is just mg, which is going to be close to 900 newtons. End of